Alright guys, we are going to jump into vodcast 9.1. We're going to talk about, we're going to sort of introduce the idea behind gases, which is our next unit, and talk about a few simple conversions that we're going to do with those gases. So let's jump right into it. You may remember this diagram from earlier in the year. If you look back at vodcast 2.5, we talked about a little something called, oh, that color pen is not going to work, a little something called kinetic molecular theory, okay, or KMT. And that's vodcast 2.5. You can go back and check, and I'll pop that in a little bit more legibly. But remember that the basic idea behind kinetic theory is that molecules are always in motion, or atoms, but molecules for most of what we're going to talk about. That they're always moving around, and that things that are in motion have what we call kinetic energy. Okay? And so we said that things that are solids, they're not moving very much. In fact, they're kind of vibrating in place. And then things that are liquids are moving around a little bit. They can kind of get around each other a little bit, but they're still not really moving around too much. And then gases, they're moving around a lot. And if you remember back in that vodcast, or in that section, we talked about the fact that gas particles, since they are in motion and they're not really connected to each other, they're moving all around, they're expanding to fill their container and all of that stuff. You may recall that we said that kinetic energy was tied directly to the idea of temperature. Okay, and so as the temperature increases, in other words, as we go from down here at some certain temperature to up here, that we can go through phase changes. And so if we were talking about something like water, the boundary here between solid and liquid we would know is our melting point. And so that would be 0 degrees Celsius, and then between liquid and gas would be 100 degrees Celsius, and that's our boiling point. And another temperature that you need to know about a lot when we're talking about the gases or really phases of any kind is that way down here at the bottom, like the very bottom of any sort of solid thing, there is a little temperature down here that is at negative 273 point, I want to say 15 degrees Celsius. That temperature has a special name. It is called absolute zero. Some of you all probably heard of this before. What absolute zero is, and the reason it's called absolute zero, you're like, well, that's not zero at all, because that temperature is 0 Kelvin, okay? And it's called absolute zero because that is the temperature at which all kinetic energy basically stops, that the molecules don't have any more motion at all, and so all molecular motion stops. Never reach that. We only know that it's there because we can sort of extrapolate on a graph, and we'll talk a little bit more about that later. But just keep that definition in mind. So, since we're going to be dealing a lot with temperatures, we need to know a couple of important temperature conversions. We're not going to worry that much about Fahrenheit to Celsius. I know that you probably learned that back in middle school, but we're in science class. We don't really use Fahrenheit. It's kind of a handy thing to sort of know because the weather reports it, but we're mostly concerned with Celsius and Kelvin. So, here's the temperature conversion that you need to write down. To go from Celsius to Kelvin, so if we have degrees Celsius and we want Kelvin, what we do is we add 273. Now that kind of makes sense if we jump back to that last slide there where we had absolute zero, okay, negative 273, right? So Celsius plus 273 is going to give us our Kelvin temperature. Now you'll note that there's no degrees Kelvin, but that's how we get there. So that's pretty simple. If we took 50, okay, so we had 50 degrees Celsius, and we add 273 to it, punch that in your calculator or do it in your head. That, believe it or not, is actually possible. We get 323 Kelvin. You'll note that there's no degrees there. Okay, it's just Kelvin. There's no degrees at all there. Okay. Now, we can also go from Kelvin back to Celsius if we need to, and that conversion works like this. The degrees Celsius is equal to Kelvin minus 273. Now, that obviously is the same equation. We just solved for degrees Celsius, which meant we subtracted 273 from each side. So if we had 600 Kelvin and we wanted to find out our degrees Celsius, we would then take 600 minus 273, okay? And so what's that going to give us? That is going to give us 327 degrees Celsius, okay? Pretty straightforward, okay? So that's temperature conversions. We'll obviously practice a few of those. The second really important thing about gas is temperature. Obviously, we sort of talked about kinetic molecular theory. One thing we didn't talk about is pressure. So what I want you to do, you may remember this little diagram, again, from that video 2.5, but So picture these as gas molecules, and they're going all over the place. And what I want you to notice is that occasionally they are running into the sides of the container. Okay, so you see them hitting the sides and bouncing off. Whenever gas molecules hit the sides of a container, or run into you, or run into the table, the desk that we're sitting near, or anything like that, they create pressure. Now, what pressure is pressure is a force over a given area. Okay. So it depends on what the area is. So like maybe we say that it's over, say, a square centimeter. So like we got 1 centimeter on each side, and we're going to measure how many collisions, so how many gas particles hit that thing, and how much force they impact it with. Okay, the greater the force, in other words, the faster they're moving, the more force that they're going to hit it with, and therefore the higher the pressure. Okay, and we're going to get a lot more into pressure in our other parts of our lesson, because we're going to see that it's related to temperature. It's going to be related to volume also. We will see probably tomorrow. Now, much like temperature, there are a lot of different ways that we can measure pressure, and these are sort of the most common ones. Okay, these are not by any means the only ones, but these are the ones that we typically see. The weatherman on the news uses a little something different too, and we'll talk about that. So this is kPa is kilopascals. Atmospheres is really the easiest to use. That's the one that we kind of prefer. Torr and millimeters of mercury, mmHg, Hg is the symbol for mercury, so millimeters of mercury. Torr and millimeters of mercury mean the same thing. We're not going to get much into it, but the way they used to measure pressure is that they have a big column of mercury set up. Okay, the way they made their first barometers was that they would have a tube, and then down at the bottom of the tube, there would be like a little pool of mercury down here, okay, mercury, the metal. And so the mercury would be so far up the tube, depending on how much air pressure was pushing down on it. Okay, this is called a Torricellian barometer, I think is what it's called, and that's where the word torr comes from. It's from Torricelli. And so as the air pressure presses down on the mercury, it makes it go up higher. So if there's more air pressure, then the mercury that day goes up some. And if there's less air pressure, then it goes down some. And that's where this millimeters of mercury and torr comes from. And in fact, if you watch on the news, what they'll talk about is pressure in inches, or they might give the symbol for inches like that. It's the same thing. It's inches of mercury, basically, is what they're measuring it by. Okay? Anyway, for us, we've got a few conversions then to do, okay? So, you see this big, long equality, and you're probably thinking, oh my gosh, do I have to use all of that? No, not at the same time. You pick the two that you need. So let's do some conversions. If we had 450 torr and we wanted to turn that into atmospheres, how would we do that? So I look up here and I find torr, okay, and I find atmospheres, and so basically I sort of box that part out, and that's the part that I'm going to use for this problem. So how do I solve that? I solve it the same way I would any conversion factor problem. I have 450 torr, okay, and then I know that 760 torr. Why would I put that on the bottom? Because this way I get torr to cancel out, and on the top of that goes 1 atmosphere. Now, why did I pick 1 atmosphere? Because the problem asked me for atmospheres. That's my unknown, okay? Your relationships are always between your given and your unknown. My given is torr, my unknown is atmospheres. So I punch that out, and I get as my answer 0.59 atmospheres. Okay? So pretty straightforward. Let's work another one real quick just to make sure that we sort of got the concept. For the next one, we got 450 torr, but we want to turn it into kilopascals. So in this case, I've got 760 torr and 101.3 kilopascals. So I may want to sort of rewrite that to make sure that I know exactly what my equality is, since they're not right next to each other. So we got 101.3 kilopascals, 760 torr, okay? And then we're going to plug that one in. So we've got our given again, 450 torr. I want torr on the bottom again. Why? Because that's what I want to cancel. So 760 torr. And on the top of that, obviously, goes my 101.3 kilopascals. Again, why did I put kilopascals here? Because that's what my unknown is. Okay, that's what I'm looking for. So we punch that in the calculator, and we get, I think we get 59.9, but since we have 2 sig figs here, I'm going to round to 2 sig figs, and that's going to be 60 kilopascals. Remember, that decimal makes that 0 significant. All right, so relatively straightforward. What we want to talk about is something called STP. Now, STP, what that means is that it stands for Standard okay, or like normal, that's what the word standard sort of means, temperature, and pressure. Now, that kind of makes sense. We've talked about two things so far, right? Temperature and pressure. And what this is it sort of sets up a normal way that we want to talk about these things, okay? What is the norm? Okay, so the normal part here is going to be what temperature and what pressure do we want to take a lot of measurements at, because we can tell certain things there. So the way this is defined is that standard temperature is 0 degrees Celsius. Okay, now what is 0 degrees Celsius? That actually means 273 Kelvin. Now, why did they pick that? Because that's freezing point. I don't really know. I mean, to me, it probably would have made a little bit more sense to make it probably about 298 Kelvin or 25 degrees Celsius, because that's kind of close to room temperature. But I guess that depends on the room you're on. So they picked something a little bit more standard, which is the freezing point of water. So 0 degrees Celsius is standard temperature. Standard pressure is 1 atmosphere. Okay, and of course, if it's 1 atmosphere, that also means that it's 101.3 kilopascals, okay, or 760 torr, okay? But the way it's usually defined is 273 Kelvin and 1 atmosphere, okay? That's standard temperature pressure. Now, why does that matter to us? Because at that STP, okay, or standard temperature and pressure, this is true. 22.4 liters of any gas. It doesn't matter what gas it is. It could be something pretty heavy like sulfur hexafluoride. It could be something really light like helium. Doesn't matter. As long as we have 1 mole of it, its volume is going to be 22.4 liters if we're at standard temperature and pressure. In other words, if we're at 0 degrees Celsius and 1 atmosphere. Okay, it doesn't matter what gas it is. This is actually where Avogadro of the number fame, this is where he sort of comes into view here. He's the guy that comes up with this whole idea of standard molar volume. Okay, so 22.4 liters equals 1 mole. Now, this is a super easy conversion that you're going to use in all kinds of volume problems. If you're at STP, okay, now usually the problem will say it. Okay, so like here it says how many liters are in 4.500 moles of oxygen gas. Technically, the problem should say at STP, but if there's nothing else given to you and it's just moles or liters, you can probably assume. And we'll talk about cases tomorrow and the rest of the week where that's not true, but most of the time this is pretty valid. So we're going to work this like we have most of our conversion factor problems all year. I've got a given 4.500 moles of oxygen. Now, why would I put all those zeros? Remember, that's 4 sig figs that way. You'll see why when we get the answer here in a second. And what am I looking for? How many liters? Okay, so I'm looking for liters of O2. Now, since it's at STP, then I'm going to use this. Okay, so that is the only equality that I need for this particular problem. So 4.500 moles of O2, okay, is that, and we've got 1 mole on the bottom. Why 1 mole? That way moles will cancel. On the top is 22.4 liters. Punch that into your calculator, and what do we get? We get 100.8 liters of O2. Remember, ever since stoichiometry, it's real important to label what chemical it is, okay? So, pretty straightforward. As long as you're at STP, you can make that easy calculation. We'll see later this week what we do if we're not at STP. But for now, we're going to talk about what do we do at STP. So, how many grams of oxygen are in 50.0 liters of O2? Again, it should say at STP. If it doesn't, you can probably assume, as long as there's nothing else going on, as long as it doesn't give you another pressure or give you another temperature, which is what we'll see in the problems later on. So my given, 50 liters of O2. Now, my unknown this time is grams of O2. Now, I don't know how to go from liters to grams, but I do know that I can use this if I'm at STP. 22.4 liters equals 1 mole. Okay, and I'm going to label that O2. And if anytime I can get to moles, how do I find my way to grams? Yeah, molar mass. So 32.0 grams, I just did it like a total Dora the Explorer thing there. I paused to let you answer it because I'm sure that's what you were doing. So 32.0 grams of O2 equals 1 mole of O2. And so there we can go from liters to moles, moles to grams. That's all the wonderful conversion stuff that we need. And that was the worst straight line ever for railroad tracks. So 50.0 liters of O2. I'm going to get rid of liters first, so I'm going to put 22.4 liters down here. Again, I'm going to keep labeling everything, because since we've done stoichiometry, we know that it's pretty important to not only put units, but to put what chemical it is, because that can change, and it will in a couple of days for some of us. And then we put the molar mass over here. Now, why did I do that? Because I'm getting rid of moles, because I want grams. Okay, so grams of O2 is what my answer is going to be in, and we punched it into our calculator, and we get 71.4 grams of O2. All right. Simple as that, guys. Again, as with everything else we've done this year, you got to work through the practice problems and make sure that you know how to do each of these problems. Shouldn't be that difficult as long as you actually work through all the practice. Thanks, guys.